In this lesson, you will need the Ep.16. We shall look in detail at each of the multi-engine piston aeroplane graphs. When you are ready, turn to Section 3, Page 3, Figure 3.1. Figure 3.1 allows us to calculate the fuel, time, and distance required for the initial climb. Using the examples shown on the graph, we will assume a climb from mean sea level. Enter the graph with the cruise outside air temperature, in this case -13 degrees Celsius, and go vertically to the cruise altitude of 16,500 feet. Go horizontally to intercept the fuel, time and distance curves. From each of those curves, go vertically down to read off the relevant figures on the bottom scale. In this case, 15 gallons, 27 minutes, and 50 nautical air miles. If we need to calculate a climb from an airfield above mean sea level, we use the same graph, but in addition to the cruise details we entered in the last example, we also enter the airfield data. In the example shown, the departure airfield altitude is 2,000 feet and the outside air temperature is 21 degrees Celsius. Enter the graph at the airfield temperature and go vertically to the airfield elevation. From this intersection, go horizontally to intercept the fuel, time, and distance curves. Now go vertically down to read off the fuel, time, and distance figures, which in this case are 2 gallons, 3 minutes, and 5 nautical air miles. Subtract these figures from the climb from mean sea level to obtain the correct figures for the climb from the airfield to the cruise level. When you are ready, turn to Figure 3.2. From Figure 3.2, we can calculate the still air range of the aircraft with and without reserve fuel. The left side of the graph gives the range at various power settings, with 45 minutes reserve. However, the reserve fuel of 45 minutes assumes a power setting of 45%. On the right side of the graph are the figures for range with no reserve. In the introduction lesson on this section, we saw that the power is shown as a percentage of full power. These power settings are shown in the top right-hand corner of the graph. To find the range for a given power setting, enter with the cruise altitude and go horizontally to intercept the power setting curves. From the intersection of the two lines, go vertically down to read the range with reserve fuel on the left of the graph, or without reserve fuel on the right of the graph. From the example given, we find that the range at 45% power at 16,500 feet with reserve fuel is 942 nautical air miles, and without reserve fuel, 1,060 nautical air miles. The range found is the range in nautical miles in standard temperatures. It includes the climb and descent distances. For non-standard temperatures, the range is adjusted as shown in the box in the top left corner. It states that the range increases approximately 1 nautical mile for each degree Celsius above ISA, and decreases by the same amount for each degree Celsius below ISA. Range is affected by wind, so it may be necessary to make a further adjustment of nautical air miles to nautical ground miles. When you are ready, turn to Figure 3.3. Figure 3.3 is used to calculate the fuel flow in US gallons per hour and the manifold pressure for standard temperatures. Enter the table at the cruise altitude, for example, 6,000 feet. Then go right to the appropriate power setting block. Let us assume 55%, and then read the fuel flow in US gallons per hour, which in our example is 18.7 gallons per hour. In the same power block, select the column appropriate to the engine RPM, say 2,400. And where this column intersects the pressure altitude row, read off the manifold pressure. Since these tables are for standard pressures, it is necessary to correct the manifold pressures for non-standard temperatures. Paragraph 4.1.2 states that to maintain constant power, the manifold pressure must be corrected by adding 1% for each 6 degrees above standard and subtracting 1% for each 6 degrees below standard. When you are ready to proceed, turn to Figure 3.4. One of the factors required to convert nautical air miles to nautical ground miles is the aircraft's true airspeed. To find the true airspeed for a given cruise altitude and power setting, enter the graph with the cruise outside air temperature and go vertically up to intercept the pressure altitude line. From here, go horizontally to intercept the appropriate power line, and then vertically down to read off the true airspeed. Figure 3.5 is a means of calculating the aircraft's endurance in hours and decimals of an hour for a given cruise altitude and power setting. The left side of the graph gives the endurance at various power settings with 45 minutes reserve fuel. However, the 45 minutes reserve fuel assumes the power setting is then set to 45% power. This is known as safe endurance. On the right side of the graph is the endurance without reserve fuel, known as total endurance. Enter the graph at the cruise altitude and go horizontally to intercept the power lines either with or without reserves. From the appropriate power line, go vertically down to read off the endurance with reserves on the left of the graph, or without reserves on the right of the graph. Endurance is not affected by wind, so no corrections are necessary. The final figure in this section, 3.6, gives us the values for fuel, time and air distance to descend from cruise pressure altitude. We shall first calculate the figures for descent to mean sea level. Enter with the cruise outside air temperature and go vertically to the cruise altitude line. From this point, go horizontally to cut the fuel, time and distance lines. From each of the fuel, time and distance lines, go vertically down to read off the appropriate values. If the descent is to be made to an airfield above mean sea level, first carry out the procedure just described, then re-enter the graph with the airfield outside air temperature and go vertically to the airfield elevation. Go horizontally to cut the fuel, time and distance lines. From each of the fuel, time and distance lines, go vertically down to read off the appropriate values. Subtract the values found from the corresponding values for descent to mean sea level. The result gives the values for descent from the cruise altitude to the airfield. Once again, it may be necessary to correct the distance to nautical ground miles. This concludes the explanation of the graphs for the multi-engine piston aeroplane.